Welcome to Applied Materials and Corrosion. Today we're going to think about how pH affects corrosion. We already did an experiment to show that there is an effect, but now we're going to think about a way to present that information in an easy to read fashion. So you will be familiar possibly with phase diagrams of metal, so let's have a look at one now. On these type of phase diagrams we have the composition across the bottom axis, across the x-axis, and in this case the temperature on the y-axis, but that is not the only type of phase diagram that we can make. So if we look at a chemistry phase diagram, we might have liquids mixing, so a composition axis, and we could have more than one of those. So if we have water, oil and soap, we end up with a ternary phase diagram, so we have three of these axes, and we may decide that that's too much information, so we don't want a temperature axis as well. Those phase diagrams you can also look up. We're not going to do those right now. We're more interested in a phase diagram that includes the information that we want for corrosion. This was the first hit I got on Google. It's called Eutictic Solder, some soldering company. But what I'm interested in is this type of diagram. So this is a typical phase diagram of metals. In this case it's tin and lead. So if we take this, we can see that it's a thermodynamic diagram. You may remember that to measure this diagram we take any mixture and we keep it at some temperature for a really long time, theoretically infinity time, and then we'll get a mixture of products. So if we're above this liquidus line, which goes down here, and up here we just get a liquid. So up here we've just got liquid, down here we've just got solid. In the grey areas we have a mixture of solid and liquid. No, below this line we have a mixture of solid and liquid, and here we have a mixture. Oop, I've made a mistake. Let me try again. So if we look above this line we have just a liquid, everything is molten. Below this line this is solid, and then we have mixed phases in the other parts of the diagram. So if we sit here we would have some lead with a bit of tin in it, this alpha lead, plus liquid. If we go over this side where we've got a lot of tin, we get tin crystals with a little bit of lead in, plus lead. These little fillets show the solubility. So if we have here, we've got lead with a little bit of tin in it up to this point, so we can get about 18% of tin in our solid lead before it separates, and we get before it separates, and we get a stronger concentration of tin in the liquid and a lower and a higher concentration of lead in the solid. This is a thermodynamic diagram, so effectively if we go here and we have a solid, it is implying that we wait for infinity time. You may have used these diagrams for kinetics, so very often in metallic materials we use these diagrams to predict what will happen if we don't cool down infinitely slowly, because that's practically very difficult to do. So if we sit here and we cool down very fast, we can jump straight to here. We don't make these crystals of lead beforehand. If we cool down slowly, we make these crystals of lead. That causes us to go down this line. So we increase the concentration of tin in the solution, and we're making lead, alpha lead crystals of this lead with a bit of tin in, that either sink to the bottom or float to the top depending on whether they're more or less dense. When we get to this, the eutectic point, it will cool down straight. If we cool it quicker, we can force it past here. We can make things that are thermodynamically unstable, so we can freeze in our mixture. So now I've switched to a different type of diagram, the Pourbaix diagram, And this is on Wikipedia. This is the English version of Wikipedia, but it doesn't really matter. This is the diagram on Wikipedia. I would like to show you the author information because it's only fair. Where is it? Here. Damn it. So this is where the data comes from. That will be the author of this diagram. So on this type of diagram, we have a very similar structure. It looks quite similar to the normal phase diagram, but in this case we have two different axes. We have pH, which is similar because it's a concentration scale, and on the vertical axis we have voltage. So if we think of a normal electrochemical cell, we could see that the composition inside the cell, the composition of the liquid phase would be on the x-axis, where in this case we're just considering pH, and on the vertical axis, on the y-axis, we have the voltage that we apply to the electrode. So let us imagine we're going through this diagram. So we start off at the bottom. Let's take a pH, let's take pH 7 because that's fairly common. So at pH 7, if we have our ion at a more negative potential than minus 0.5-ish, it will stay as ion 0. It's a thermodynamic diagram, so that means if we theoretically held our ion at that potential forever, nothing would ever happen to the ion. It would stay as ion 0. It doesn't mean it won't move around, but it will stay thermodynamically as ion 0, so it is stable. If we hold it at a potential of 0 volts, it will dissolve into the solution as ion 2+, and this is assuming that we have infinite solution. So if we do that and we sit at 0 volts forever, we will get only soluble ion 2+ as our product. If we go higher in voltage, if we make it more positive, we'll form iron oxides instead. So if we go all the way up to the top to at pH 7, it'll be about 1.2 volts, no, a bit lower than 1.2 volts. We get iron oxide, FeO4 2-, which is also soluble. In between that we make a solid form, Fe2O3, with water, so we make rust effectively. If we make our solution more acidic to pH 4, which is what we did, we tend to avoid the iron oxide, the rust phase, and dissolve straight into solution, so we can see the Fe2+ part is bigger. It's more easy to make iron 2+, and if we go to pH 3.5 or less, 3.8 maybe, we miss it entirely. We go Fe2+, Fe3+, FeO4 2-, so there are only soluble species of iron. If we make it very basic, so if we go all the way to, well, let's make it a little bit basic. If we go to pH 12 and we sit at any voltage between, let's grab it, any voltage between 0.6 and minus 0.6-ish, we will make solid products. Our iron will fully turn into one of these solid products, so either iron oxide with water, Fe2O3 with water, or Fe3O4, or iron hydroxide. But it will turn it fully into those products over time because we're looking at a thermodynamic diagram. Obviously, if we have a higher potential than that, a more positive potential, we will make this negative ion up at the top. What does it mean for kinetics, however? If we make a solid product, iron hydroxide, iron oxide, then it will interfere with the reaction and slow it down. So if we have a pH of 12, for example, or 10 even, which is what we had, we would expect to form iron hydroxides on our iron at various potentials. So as long as our potential is below 0.7 volts, and it's not got a scale of what it's compared to, but it's compared to normal hydrogen electrode. If we have a potential of below 0.7 volts, we will tend to hinder the corrosion, and some of these corrosion products are better at doing it than others. So as we saw in our measurement, iron at pH 10 doesn't corrode as fast. The current on an iron electrode at pH 10, even at positive voltage, is not as high as the current on an iron electrode at pH 4, and that's because we are forming insoluble species which are getting in the way, and that's what this diagram shows us. What it also shows us is that there's a little crack down right at extremely high potential. It's the smallest writing on the whole diagram, HFeO2-, so if we make it very basic, we can have a problem, but if we jump in potential, we get back to a solid product. So there is a little weird part in the iron curve. That is quite common for metals, so I'll find you another one now so we can talk about that. This is another example of a Pourbaix diagram for aluminium, and in this case the aluminium corrodes both at high pH and at low pH, because as we know from home, if you put it in the dishwasher, if you put something aluminium in the dishwasher, it goes black. That's because the pH is higher than the passivation region, which is around somewhere between 5 to 9 for aluminium. Above pH 9 it corrodes, it says corrosion, but above pH 9 the stable form of aluminium in water is the aluminate anion. Below pH 4 the stable form of aluminium in water is the aluminium 3+ ion, so it also corrodes very strongly. Here it says corrosion, passivation, corrosion. There are two dotted lines on this diagram which we should probably address. So here once again in Wikipedia is the diagram just for water. This is where the two dotted lines come in. So we take the bottom dotted line, we can see it's a reaction between H+ and electrons to form hydrogen. If we imagine that reaction, we can see obviously from a Nernst equation point of view that it's going to be directly controlled by the concentration of the H+ ion. So obviously if it's more acidic, it's going to be easier to do that, so we won't need such a negative potential to force the electrons onto the hydrogen ions. Remembering the Nernst equation is a log relationship, so it's the log of the concentration divided by the log of the other concentration, so the log of the concentration of the hydrogen and the log of the concentration of the H+ ions. But in this case the concentration of the hydrogen is constant, it bubbles away, it's not going to stay there. So the concentration of the H+ is important. That is obviously would generate a curve, however pH is also a log function, and so the two log functions cancel each other out and we get a straight line. That's why this line is sloped. So that tells us that below that line our metal, any metal that comes below that line, will react with the water, will tend to react with the water and form hydrogen. Obviously it can be covered with an oxide layer and not do it very fast, but thermodynamically, because it's a thermodynamic diagram, thermodynamically that is what should happen in the end. The second line on here is the reaction of oxygen with water, in effect, water and electrons to form water. Now we're either forming hydroxide ions or we are forming water from hydrogen and oxygen. You can see there are two reactions there depending on the pH. Again, H+ or OH- are part of the reaction, so the concentration is in there, so that's why it's sloped. And in this case the concentration of oxygen and the concentration of H+ are controlling the reaction. So they've drawn the line, one assumes, for a concentration of oxygen at 1 atmosphere. So this top line is if we take our iron and we put it, or whatever, our metal, and we put it into water close to the top of the water where oxygen can diffuse in, if it is below the top line, the oxygen will tend to react with the metal to to take electrons from it. So the oxygen will tend to take electrons from the metal to cause it to oxidize. If it is in a situation where there is no oxygen in the water, so in a bioreactor at the bottom of the sea, the bottom of a lake, we are in a different situation where that reaction can't happen because there is no oxygen, or the concentration of soluble oxygen is very low, so therefore that reaction is pushed much lower in voltage. And that means the other reaction that can happen. So if we have an implant inside the body, it could be subjected to either of these two reactions, depending on where it is and depending on the local conditions. So going back to the aluminium case, we can see that aluminium, this immune part of aluminium, the voltage at which aluminium wouldn't corrode, is well below either of those two lines, which means if we put a voltage onto aluminium in order to make it thermodynamically immune, in order to make it 100% stable in water, the water would break down. We would be breaking the water into hydrogen the whole time. We would first of all use up all of the oxygen dissolved, and then we would start to break the water into hydrogen, because aluminium has a high enough electropotential. If it was clean, it would have a high enough negative electrode potential to form hydrogen in water. We can see that relatively easily on this diagram if the immunity line is below the bottom dotted line. So here is a diagram for iron with the dotted lines included from a review, which is interesting for us. Let us have a look here. You can see the top line is for oxygen oxidizing it, and the bottom line is for the water turning into hydrogen. So we can see that at low pH, we can make hydrogen using iron. So the iron can dissolve to form iron 2+ and make hydrogen out of the water, but at high pH it comes right inside the solid forming region and chooses, by the voltage that we generate from the water, it will determine which of the corrosion products that we get. So instead of making rust, Fe2O3, we make Fe3O4, because deoxygenized water is not capable of doing that. And that is one of the reasons why ships and things that sink to the bottom of the sea last a surprisingly large amount of time, because instead of corroding to form the normal type of rust, Fe2O3, with water on, which is not very protective, it forms better types of rust like iron hydroxide and iron magnetite, Fe3O4, which are much better at preventing the metal from corroding. It doesn't stop it forever, as you can see, because the immunity line is still below it, but it does slow it down. If we took a even less reactive metal, such as copper or silver or something, we would see that it crosses the hydrogen line, and sometimes it crosses even the oxygen line for noble metals like gold, for example. So if we look at this diagram, we can see that copper is completely stable. It will never corrode. Thermodynamically stable means it doesn't matter what you do, it will never corrode in deoxygenated water. That's the bottom green dotted line. So if we put it in deoxygenated water, it cannot give its electrons to the water to make hydrogen. It is thermodynamically impossible. So the copper and the water will stay together friendly forever. Nothing will ever happen. But the top dotted line, if there is oxygen in the water, the copper will corrode, And depending on the pH, we will either have, well, we'll have one of three situations. We can have complete corrosion at low pH to copper 2+, where the oxygen is reacting effectively with the copper to form copper ions and hydroxide ions. If we take a medium pH, we will tend to form solid copper oxides on the surface, which kinetically will slow it down quite a lot, so that's a very common situation. And if we have high pH, it will become completely unstable again. The copper will dissolve as copper hydroxide, as a cuprate anion, but it has to be extremely high pH. You can see our pH scale goes to 14, which is crazy. The interesting part is if we put copper into a closed container of water, it will use up all of the oxygen and then the reaction will completely stop. So if we put other ions in there, we can modify this diagram somewhat. So if we take an ion in the sulfate conditions, we can form various solid sulfates, which will change the shape of our diagram somewhat. So we will need to look up a new diagram or make a new diagram for the conditions that we're in. In this case, so I hope that's a good introduction to this type of diagram. It is important to me that you understand them, because this is really an easy way to predict what metals are going to do in different conditions, and it's a useful diagram to know how to deal with. See you next time.